Section 2.3, valid and invalid arguments. So an argument is a sequence of statements, and we will have one or more premises, which are also called assumptions or hypotheses, and we might have a few statements in between to help us get to the end, but the very last statement is the conclusion. And at the beginning of that, we'll have this little dot triangle shape, which we read as therefore. If the conclusion follows logically from the premise or premises, then that means it is valid. And we will say invalid if that is not the case. So, we are generally going to set this up with a truth table, but we can certainly use the logical arguments that we've seen otherwise as well. So, let's go ahead and take an argument and determine whether or not it's valid. So again, we're going to fill in a truth table. And we want to particularly indicate where the conclusion is. That's really the only column you need. I will usually put in the others as well, just to help see what we've got. So here is the argument that we are going to try and follow. And you can see here a description of what we're about to see. All right, so we have to make our premises. Again, our premises were these first two statements that we were given. And again, I'm going to make a couple columns to get that. And then here's our conclusion, P implies R. That's our last one. So the only ones we're going to look at are where the premises are both true. So if one or both of them are false, we're going to disregard those rows. We don't care about them. So you can hopefully see them. They're slightly light blue there. There's 4 of them. And in order for this to be valid, all of these results have to be true. However, it did not work out this way. We did have one that is false. So I would conclude that this argument is not valid or invalid. All right, I am not going to worry too much about the terms here, modus ponens and modus tollens. That is from the Latin if you're curious, but I do at least want us to see what it looks like. So the modus ponens means our premises are if P then Q, and the second one is Q. We will then, the second one is P, at which point I conclude Q. And an example, if the sum of the digits of that number is divisible by 3, then that number is divisible by 3. And the sum of the digits of that number are divisible by 3, so therefore that number is divisible by 3. And here's some examples where we would want to conclude that. So here's my if-then, and I'm given the first part, the Q, P, so I will then conclude the Q. Did I actually write out the modus tollens? I didn't actually write out the modus tollens. The modus tollens means I've got my first statement, if P then Q, but then we are given not Q, at which point I would then conclude not P, and that is modus tollens. Again, you don't need to know the names, but I would like you to see what those arguments look like. All right, so let's talk about rules of inference. How do we decide if something's true or false? So again, these two are both going to be valid. So if I've got an or, remember as long as one thing is true, it works. So if I've got P, the or is true. If I've got Q, the or is also true. And here's an example that we could say using non-mathematics. We are describing the next type as specialization. Here I've got the and. So if I have the and, I have both of them individually. So I'd have both the P and, as it turns out, the Q. And an example of that, Anna knows numerical analysis and Anna knows graph algorithms. That means Anna knows graph algorithms. We will sometimes use that phrase in particular because presumably that's the part of the argument argument that we actually care about. All right, our next technique is called elimination. So here I've got P or Q, and then we're told, okay, the Q doesn't work. Well, that means the other one must. So I will include P. And we can say similar, if it's the not P, we will then take Q. So if we know that x minus 3 is 0, or x plus 2 is 0, and we also know that x is not negative, we would then know x is not negative 2. We would then conclude the other statement that x minus 3 equals 0. And again, we call this technique elimination. Our next one is called transitivity. So P implies Q, Q implies R, therefore P implies R. We've got that chain of if-then statements. So our example for this, if n is divisible by 18, then n is divisible by 9. If n is divisible by 9, then the sum of the digits of n is divisible by 9. So here's P, here's Q again, here's R. So I use transitivity to say if n is divisible by 18, then the sum of the digits of n is divisible by 9. We also have something called cases. So here we've got P or Q. We're told that P implies R and Q implies R. So basically, no matter which one we've got, we're going to end up at R. So my conclusion is that R must be the result. So here would be an example of something with cases. We're told that x is positive, or x is negative. If x is positive, then x squared is positive. If x is negative, then x squared is positive. So in other words, it doesn't matter whether my number is negative or positive. Regardless, my x squared is positive. And that is an example we have definitely seen in mathematics. Here's a slightly more complex one. Here, there's a lot of things going on. So if you can follow all of those if-thens, and then you'll notice we've got a couple where we're telling it's not the case. You'll notice we've also got an or in here. So again, this one is a little bit more complicated. But if you read through all of that, and here's logically then how I would represent that. So that first statement, we've got RK implies GK. GK implies SB, therefore RK implies SB by transitivity. We're also told that RK implies SB, we just have that, not SB, therefore not RK. And we've got RL or RK, and again, we know it's not RK, so therefore RL. And finally, RL implies GC, using what we've already said. We know RL, therefore GC, and my conclusion is that they're on the coffee table. So that is a much more complicated one. Generally, we are not going to have to do anything with that many steps. But I did want you to see at least one example of it. All right, let's talk about fallacies. In other words, this time it doesn't work. This is when we basically make a mistake. Our big ways are using an ambiguous premise, using circular reasoning, and jumping to a conclusion. We've also got a couple types of errors as well. And needless to say, our actual argument might be true, but it is not valid because we are using one or more of these fallacies. So let's start by showing what we call the converse error. So we'd say if Zeke is a cheater, then Zeke sits in the back row. Zeke sits in the back row, therefore Zeke is a cheater. So here I'm saying the Q, the then, is true, and I'm trying to back that to the original. And that is what we call the converse error. And again, this is the general form of that converse error, and again, this is logically invalid. Let's look at the inverse error. If these two vertices are adjacent, then they do not have the same color. These two vertices are not adjacent, so I've got not P there, And I conclude then these two vertices have the same color, so I am concluding not Q. So again, that is using the inverse, and once again, that is also something I'm not allowed to do. All right. Here's an example where the argument is valid, but because the premise is false, we have a problem. If Canada is north of the United States, then temperatures in Canada never rise above freezing. Canada is north of the US, therefore temperatures in Canada never rise above freezing. Canada is cold, but it definitely does get above freezing. So when we're making arguments, we do also want to have premises that are true. So now let's look at an invalid argument where my premises are true, and I've got a true conclusion. Here we've got the converse error. However, the conclusion is true. If New York is a big city, then New York has tall buildings. New York has tall buildings, therefore New York is a big city. So New York is definitely a big city, but if we follow this using the rules of logic, this is still an invalid argument. We've got a converse error. So I can say a true statement, but I still have an invalid argument. And we can also use that term sound, where we say it is not only valid, but all of the premises are true. And needless to say, we want sound arguments. All right, let's also look at some contradictions and valid arguments. So, if we can show that this statement P leads logically to a contradiction, we can then conclude that P is true. So basically what we're trying to do is we take the opposite of P. We take not P, and we follow things, and we hope to get a conclusion. That will then conclude that P itself must be true. And later in this class, we will do proofs where we will use this technique, and those are called proof by contradiction. We'll spend a whole section on that. And here is the truth table behind that, so you can see P, not P. Remember, contradictions are always false. Here is where my premise is true, and that does give me the true conclusion. So I am allowed to do that. Here's a quick example of that. This is a logic problem you may have heard, although it's often phrased in different ways. And how do you then figure that out? And I'm just going to kind of skim through this so you can see how what we determine works and what does not work. And here we've got a contradiction. So if we start by the contradiction rule and go by then, we do conclude that B is a knave, which is what we are hoping to conclude. And here's just finally a quick summary of all of our rules of inference. Again, you do not need to know the names of these, but we do at least in general want to be familiar with what they look like, and you are going to see many of these examples as you work through the homework. And that is everything in section 2.3.